move in a linear motion, we talk about linear velocity, linear acceleration, and linear displacement. Now we also have objects that go in a secular motion. So anything that is rotating about a fixed point, then we have rotational motion. And the reason we need to use the rotational values is because if you have a circle, suppose this is a DVD disc and it's turning around, if you find the velocity here and you find the velocity here, the linear velocity, it will be different. Okay, that is the reason why we need to use angular velocity. So when you find the angular velocity, it simply gives you the speed with which the whole disk is rotating. So irrespective of which point on the disk you find, your angular rotation, angular velocity is the same. So the most basic formula is derived from the fact, if you go in a circle, if you have a circle that has a radius r, okay, and if you start at that point and you travel like that around the circle, the distance you cover, okay, a linear distance is the circumference of the circle, and the angular displacement is that symbol there. And the way we find theta is linear displacement divided by r. Okay, and then from there we get that linear displacement is equal to radius multiplied by angular displacement. And similarly, when we talk about linear velocity, it is equal to r multiplied by angular velocity. And when we talk about linear acceleration, it is equal to r multiplied by angular acceleration. So you need to know these symbols. These are angular acceleration, angular velocity, and this is angular displacement. Now, the three equations of motions that we apply to linear motion, it still applies to angular motion. What we do is, instead of writing it in terms of its angular variables, we write it in terms of its rotational values. So the formula we have, the first one, v is equal to u plus 80. The equivalent of this equation in rotational dynamics is omega f is equal to omega I plus alpha t. Can you see each of the values have changed with its respective angular values? So you know velocity, that's linear velocity, it's replaced by rotational velocity. When you look at acceleration, it is replaced by angular acceleration. So similarly, when we have s is equal to ut plus half at squared, here in terms of its angular values, its angular displacement is equal to omega I t plus half alpha t squared. Okay, the other thing of importance is that your angular rotation is given in radians per second. So sometimes in the question you'll be given the rotational velocity is given, suppose, as 5 revolutions per second. Okay, so you need to change this to radians per second. Okay, and the way you do that is, you know that 1 revolution is equal to 2 pi radians. Okay, so if you do 5 revolutions per second, you multiply by, you put the revolution in the denominator, you put 2 pi radians on top, the revolution cancel, you get 10 pi radians per second. It's very important that your angular velocity is in radians per second when you do your calculations. If it's revolutions per minute, you'll have to change it to radians per second. Okay, the other two from rotational that is covered is the concept of rotational momentum. Okay, so similar to linear momentum, which we say momentum is equal to mass times velocity. We have linear momentum with the letter L. It is equal to the equivalent of mass in rotational is what we call moment of inertia. Okay, so moment of inertia and velocity, you know, is omega. So that is how you find linear momentum. Moment of inertia multiplied by omega. And the conservation of momentum in linear, you know that momentum before collision is equal to momentum after collision. In rotational, it applies as well. So your momentum initial is equal to momentum final. So your I omega initial is equal to I final omega final. Okay, and also the concept of kinetic energy will be tested. So you know kinetic energy in linear is equal to half mv squared. So kinetic energy rotational is also equal to half the equivalent of mass in rotational is I, moment of inertia, and you'll have omega squared. So that's how the formulas are formed. Okay, so if you understand what I've just done, okay, it will be very easy for you to remember the formulas in the exam, because formulas won't be given. Okay, so try to get an easy way to actually remember the formulas. Okay, what I've done is I've got a few questions from past year papers and from your tutorials that I'll solve so that things become clear to you. Okay, so this is a question from 2011 final exam. Okay, it says a wheel is turning with the angular velocity of 10 revolutions per second. What angular acceleration is required to bring it to rest in a time of 20 seconds? Okay, so if you look at that, the angular velocity is given, and it says we have to find the angular acceleration that will be required to bring it to rest. That means our omega final must be equal to 0. Okay, our omega initial is equal to 10 revolutions per second. Like I said, revolutions per second, you need to change it to radians per second. So you multiply one revolution. Okay, so revolution comes in the denominator, and you know one revolution is equal to 2 pi radians. Okay, so revolution cancels. You get 20 pi radians per second. That is your initial angular velocity. Your final velocity is 0. You know that your time is equal to 20 seconds, and it says you need to find your what is the angular acceleration. So you need to find what your alpha is equal to. So looking at the three equations of motion, which has all 4 of these values, okay, 4 of these quantities, you know that it's omega f is equal to omega I plus alpha t. Okay, make sure when you do this, when you're doing rotational, you don't write v is equal to u plus at. Okay, you only use that in linear motion, but you remember this to actually remember this formula. Okay, so you put in the values. Your initial is 20 pi. Okay, this side is 0 plus alpha into 20. Okay, so if I bring 20 pi this side, it becomes 0 minus 20 pi is equal to 20 alpha. Okay, and I divide, I get minus 20 pi divided by 20 is equal to alpha. So you see your angular acceleration is equal to minus pi radians per second square. Okay, the reason why it's minus is because that wheel must be slowing down. That's why its final velocity becomes 0. Okay, then it goes on to say determine the angular distance covered during this time. So you write what are the things that you know. So you want to find your angular displacement. Okay, you already know that omega f is equal to 0, omega I is equal to 20 pi radians per second. Your acceleration has come to minus pi radians per second squared. Okay, and you have a time of 20 seconds. Okay, for this one you can use either of the other two formulas in your 3 equation of motion. Okay, you can either use that is equal to omega I t plus half alpha t squared. Okay, or you can use omega f squared is equal to omega I squared plus 2 alpha theta, and you find your theta, angular displacement. Make sure when you replace your angular acceleration, you put minus pi. Okay, you have to put the minus sign there because when you initially calculated, it was a negative answer, so you put that negative value in your equation. Okay, so I'll leave that for you to complete. Okay, so basically that's how you go about doing those questions, and those are the things that we look at. We look at if you know that your angular velocity needs to be converted to radians per second, okay, and if you know how to apply the equations to actually get your answers. Okay. Okay, second question is from the tutorial itself. In this one, you'll see that your velocities are given in meters per second. So your linear velocities are given. Okay. So one way you can solve this is actually convert all the linear velocity and linear acceleration to angular velocity and angular acceleration, or you can solve it as it is in linear form, and then your final answer you convert it to angular value. Okay, so if we read this, it says a car is traveling at 17 meters per second on a straight highway. The wheels of the car have a radius of 48 centimeters. If the car then speeds up with an acceleration of 2 meters per second for 5 seconds, find the number of revolutions of the wheel. Okay, so your initial velocity linear is 17 meters per second. Okay, so looking at the units, you should straight away know that it is linear velocity and not angular velocity. The radius is given as 0.48 meters. Make sure you convert it to meters, standard unit. Okay, if the car then speeds up, so final velocity is something we're not interested in that. With the acceleration, so again it's linear acceleration because it says 2 meters per second squared for a time of 5 seconds. Okay, how many revolutions of the find the number of revolutions of the wheel during this period. So you have to find what is your theta equal to in revolutions. Okay, this is what you need to find. Okay, now you know that theta is equal to linear displacement divided by r. So if we find s here, our linear displacement, we can actually find our theta. So looking at these 4 values that are given, vi, acceleration, time and displacement, we can use the formula displacement is equal to mu t plus half a t squared. Okay, and 17 into 5 plus half into 2 multiplied by 5 squared. Okay, so if you do that, you'll see your answer actually comes to 110 meters. Now what you do is you convert this to theta because you are interested in the angular displacement. So this is equal to linear displacement divided by r, 110 meters divided by 0.48. Okay, you end up with the answer being equal to 229.2 radians. Okay, you can check that in your calculator. Now that is not the final answer because in the question it says number of revolutions. Okay, so you need to change radians to revolutions. Okay, so what we do next is we know that 229.2 radians, we want revolutions on top, so you put revolutions on top, and you know in one revolution you have 2 pi radians. Okay, so the radians, they cancel out, and if you divide, okay, if you divide 229.2 by 2 pi, you get your theta in revolutions. So 229.2 divided by 2 pi gives you about 36.5 revolutions. Okay, now let's move on. Also have another question still on rotational, but this question deals with momentum and kinetic energy rotational. Okay, now if we read this, it says a merry-go-round rotates at a rate of 0.2 revolutions with a 80 kg man standing at a 0.2 meters from the axis of rotation. What is the new angular speed when the man walks to a 0.1 meter from the center? Assume that the merry-go-round is a solid 25 kg cylinder of radius 2 meters. Okay. Now a merry-go-round looks something like this picture. So the man is standing on the edge and then he walks towards the center. Okay. So this is the cylinder part, the merry-go-round, and this is the 80 kg man. Okay. So the first thing that we need to do is we need to find what is the moment of inertia before and after he walks. So in the first part, because you are trying to find the moment of inertia for the merry-go-round, okay, because the merry-go-round is going in a rotational motion, so that moment of inertia will be for the merry-go-round. Okay. So note that the total inertia is equal to the sum of individual inertias. What that means is that the inertia of the man from the center of the merry-go-round plus the moment of inertia of the merry-go-round itself is equal to the total moment of inertia. Okay, so if I find my moment of inertia initial, I'll do for the man, I'll use mr squared, because this is the initial formula for finding the moment of inertia. That's how you find the moment of inertia. For the merry-go-round, since in the question it says it's a cylinder, and if you check your books for the cylinder, the moment of inertia is given as half mr squared. Okay, so the initial part, the mass of the man is 80 kg, the radius is 2 squared because it is 2 meters from the center, plus half into mass of the merry-go-round, which is 25, and the radius of the merry-go-round is 2 squared. Okay, so you do that and you find what is the, okay, you find the initial moment of inertia, right? Okay, whatever you find you can put there. Then what you do is you find what is the final moment of inertia. Okay, the final moment of inertia will change as well, because the moment of inertia of the man will change because he has walked 1 meter inside. Okay, so again it will be the sum of individual moment of inertias for the man plus the merry-go-round. Again you'll use mr squared plus half mr squared, but this time you have 80 into 1 squared, because from the center he is 1 meter away from the center now. Okay, and this one stays the same, 25 into the radius of the merry-go-round is still 2, so 2 squared. So you find that moment of inertia. Okay, now what you can do is once you find those values, you can, before you can actually use the conservation of momentum rule, you'll see your initial omega is given as 0.2 revolutions per second. So you need to change that to radians per second. So it becomes 1 revolution is 2 pi radians. So revolution cancels, you get 0.4 pi radians per second. Okay, after you have that, you can now apply momentum initial is equal to momentum final to actually find your final velocity, angular velocity. Okay, so I moment of inertia initial multiplied by omega initial is equal to moment of inertia final multiplied by omega final. Okay, so your omega final will be equal to initial divided by final moment of inertia. So whatever values you have calculated initially, just put those values into the equation and you'll get your answer. Okay. So the answer comes to about 3.58 radians per second. Okay. Then it says calculate the change in kinetic energy due to this movement. So you know that kinetic energy in rotation is half I omega squared. So your change in kinetic energy is simply half I final omega final squared minus half I initial omega initial squared. Okay, so now you already have the values for I, for the moment of inertia, and also for the rotational velocity, the angular velocity. So put those values in, and you'll get your final answer. Okay, about 540 something. Okay, joules.